Hi there. Today we're going to go ahead and get our first good look at calculus in Physics 212. We're going to use a form of calculus in order to solve for the electric field caused by, at some point, caused by some configuration of charge that isn't point-like. So in other words, in the past, we've dealt with just particles, points of charge, sometimes referred to as point charges, and now we're going to deal with this wire. So this is a circular wire, and it is essentially, it has an equal linear charge density. So in other words, the linear charge density is constant, which is important for this problem. I'm really not sure how to solve it if it isn't constant. You'll notice that the calculus we use in this class is for very special cases only. So I'm sure there's plenty of integrals you could set up that would not be easily solved by hand and perhaps impossible to solve analytically. So you may need to use a computer program to get a good approximation. So another special thing about this specific configuration is that the point we're interested in right here, we're trying to figure out what the electric field, the total electric field on this point will be caused by this circle of charge. And that point is actually, well, firstly, the line that leads to the center of the circle to that point is orthogonal to the radius of the circle of wire. And so it's like right down the center, right on that central axis. So this is another important thing for this particular problem. All right, to start out, we don't really have an equation for how to solve the electric field using calculus, but we do have this this electric field equation right here. This is the equation for electric field strength. And so with calculus, I know this is not at all rigorous, but you can kind of choose one thing on each side to make a differential. And so in this case, this equation, I could write it as a small bit of the electric field, or an infinitesimal amount of the electric field, is equal to Ke, Coulomb's constant, times a small infinitesimal amount of charge divided by the radius between that small infinitesimal charge and the point we're interested in squared, right? The radius squared. And so you see now we have this equation that we can use for integrating. All right, so if we take a look over here, I've drawn this red chunk here. That's going to represent our small amount of charge. And as you can see, it's some distance r from the point of interest where we're trying to calculate the electric field at. And in this particular problem, we're going to assume that you are given lambda, the constant linear charge density, that you were given a, the distance from the center of the circle to the point of interest, and y, the radius of the loop. So these are all given. So we're going to try to calculate the E field using these values. All right, so the first step to cracking this problem is to go ahead and define an angle theta, which happens to be the angle between the opposite side and the hypotenuse, right? So between A and R. And as you can see, the angle theta is also over here. So I've drawn my little amount of electric field. The direction is important. So in this case, this radius, right, the electric field will always be collinear to that radius. It's either going to point away from the charge or directly towards the charge. And that's all dependent on whether lambda is positive or negative. So the way I'm drawing it is kind of assuming that lambda is positive. But as you'll see later on, we can solve it arbitrarily like this. And then when we plug in lambda, it will either make the E field point one way or the other. Okay, so we essentially have to figure out what's up with this one little charge, and then we have to do the same process for all such charges along the ring. So that's going to end up sweeping out a cone of electric fields, of small infinitesimal electric fields. Let me try to draw that. So there's all these different contributions from each infinitesimal amount of charge. I know it's messy, it's hard to visualize. So I'm going to go ahead and clear it up. Hopefully that helps a little bit. but we're focusing on one at a time right now. And an important step in this problem is going to be to go ahead and break down the electric field contribution due to the infinitesimal charges into their x and y components. So in this case, I should probably draw it. I'm assuming this is the x direction and this is the y direction. All right, so we can go ahead and break these into components using trigonometric functions. And so the small contribution of the electric field due to the small charge in the y direction is going to be equal to the hypotenuse, right? The hypotenuse, which is d sub e times sine of the angle theta. And the x component of the electric field contribution from this small charge is going to be the hypotenuse, which is dE cosine theta. All right, so here's another kind of tricky point to this problem, which once you know it, you'll kind of see it pop up in other places. But for every small charge, there's some equal small charge that's directly opposite of that first small charge with respect to the ring of charge. And so what you'll notice is that since there's an equal amount of charge here as there is up here, right? Because lambda, linear charge density, is constant. That means that this contribution of the E field is going to have a Y contribution that is equal and opposite to the contribution that we looked at prior. And this is going to be true for every such dq on this ring of charge. There's going to be one. Basically, if you drew a line from that charge through the center of the circle to the other side of the circle, that bit of charge, its Y contribution to the E field is going to cancel this charge's Y contribution to the E field. And so how we're going to go ahead and say that is we're going to say that due to symmetry, so by symmetry, E sub Y is going to equal 0. In other words, the total Y electric field at this point is going to be 0 when we sum up all the DEYs. So another way of saying that is that the integral of all such DEYs is going to be 0. So if that's the case, which it is here, then that means that the only thing contributing to the E field at this point in space from this ring of charge is going to be the X component. And so let's go ahead and multiply this equation right here. I'm going to multiply both sides by cosine theta because I just want to know DEX, and DEX is DE cosine theta. So DE cosine theta is equal to KE, Coulomb constant, times cosine theta dq divided by r squared. All right, a few other things. Oftentimes setting up these problems can be challenging just because of notation. So for example, in the electric field equation, the radius is the Euclidean distance, the shortest distance between the charge and the point you're interested in. But you may be tempted to label the radius of the circle little r because we're so used to doing that. In this case, I've specifically labeled the radius of the circle of wire y, and I've labeled the distance from the charged ring to this point of interest with r specifically so that it won't confuse us, and this equation will be able to use the same symbology. All right, so and of course we know DE cosine theta is equal to DEX. And so now what we have is we have an equation that says DEX equals Coulomb's constant cosine theta infinitesimal charge divided by r squared. We have an infinitesimal on both sides, and so we can go ahead and integrate. And the integral of 1 with respect to dEx is just EX, the total electric field contribution in the X direction, right? And so, I mean, just think if that kind of gets you sometimes, just think that the integral of 1 with respect to dx is just x. And then you can get kind of silly about it and say the integral of 1 with respect to a smiley face is just the smiley face. So in other words, this pattern works with every such thing, every such variable you would like. All right, so, and also think about it this way, what we just did on this side is we essentially summed up every contribution from every dq about the ring. And so, or every dq about the ring in the x direction. So now we have E sub x, the electric field in the x direction at our point of interest, is equal to the integral of Coulomb's constant cosine theta with respect to q and then divided by r squared. Okay. So then the next few questions here are going to hopefully be helpful in the future, and that is to look at, okay, I'm integrating with respect to q, okay. So let me go ahead and look at all such dq's on the circle. So for dq here, is the radius the same or different than it is for dq here? So I'll go ahead and draw this r again. And we see that, of course, the radius of the circle is still y, and the distance from the center of the circle to our point of interest is still a. And therefore, yes, the radius for all such dq's about this circle of charge is going to be equivalent. So in other words, the radius does not vary based on where our charge is at. So for that reason, it's a constant in this case. And likewise, if r is constant and we know a and y stay the same, then this angle should also, this angle theta should be constant as well. So for those reasons, this integral becomes really nice at this point. And what it ends up happening is we can pull out pretty much everything. Ke is a constant, theta isn't dependent on q, r isn't dependent on q. And so this is what we're left with. And once again, the integral of 1 with respect to anything is just that thing. So now we have Coulomb's constant times cosine theta divided by r squared times big Q, where big Q represents the total charge of the system here, the total charge of the charged circle of wire. All right, so there's probably a better way to write this, because right off the bat, we don't really know what theta or r is. We don't know what either of them is right now. We can figure out what they are. But since we were given a and y, right, a, y, and lambda are all given. And so let's go ahead and let's solve for this in terms of a and y. So using Pythagoras's identity, we know that r is going to equal a squared plus y squared, since this triangle formed here is a right triangle. And we know that cosine theta is opposite, or is adjacent over hypotenuse. The adjacent side to this angle theta is a, and the hypotenuse is, of course, the square root of a squared plus y squared. So now we can do these substitutions, and what we end up with is that the contribution of this ring to the electric field in the x direction is equal to Ke divided by r squared, which is going to just be a squared plus y squared, times cosine theta, which we found was equal to a divided by the radius, which is a squared plus y squared under the root, all times q, the total charge of the ring. And now we can put it all together. Of course, the square root of something is the same thing as it being to the power of 1/2. And so ultimately this ends up being Ex equals Coulomb's constant times A divided by A squared plus Y squared, all to the power of 3/2 times the total charge. So here's an equation, but we weren't given total charge. We were given this constant linear charge density. So how could we find that? Well, we know that lambda is defined as charge per total length. So in other words, before we said the total charge was equal to the linear charge density times the total length of the curve. In this case, it's a circle. So I've just rearranged this equation over here on the left. And the total length of the wire is going to be 2 pi r. It's going to be the circumference of the circle. And so I guess I didn't really need to rearrange it. Let's multiply both sides by 2 pi r. And so we see here that Q is equal to 2 pi r times lambda. So we could go ahead and plug this in here. And then we would have it in terms of things that we were given. Then we could just plug and chug. And of course, you could have plugged and chugged. You know, you could solve for Q externally and then just plug it in. It would probably look nicer. All right, so this is the E field in the X direction, but of course, we showed earlier by symmetry that the E field in the Y direction is 0. The net contribution in the Y direction E field is 0. And so really, EX is just E. It's the total E field at the point of interest. And we see that it's pointing in the I hat direction. So if you wanted to write this as a vector, you could say, I'm going to write it in the way I had it before I plugged in the what Q equals in terms of other things. Just looks nicer. Okay, so it's in the I direction. And so you can see now that if the charge is positive, if Q is positive, then the electric field will point away from the ring of charge in the I hat direction. And if the charge, total charge Q is negative, the electric field at the point of interest will point towards the ring of charge, or towards the center of the ring of charge. All right. I know this section, this chapter is very difficult. I remember it being very difficult. And I mean, the number of tricks that you use to get through even just this problem, I mean, there's at least 3 tricks in there that aren't, you know, just obvious. That's for sure. The only reason why I know them is because I've done the problem so many times. So I hope this was helpful, though, just walking through the process. And I'll be making another video that uses calculus as well to find the electric field contribution from a surface. All right. I'll see you next video.